Screen is visible to all of you. PPT is visible to all of you. Yes, okay. This mechanics of material is related to engineering mechanics. There is a difference between engineering mechanics and strength of material. Is that in engineering mechanics we use rigid body. Rigid body means the body does not deform under the application of load. That is known as a rigid body. And in engineering, in the mechanics of material, we consider the deformable body. Means whenever we apply the force, that body goes for the deformation. So that is the basic difference between the engineering mechanics and mechanics of material, or we can say strength of material. Right. So another name for this mechanics of material is the solid mechanics. Okay. Now in today's lecture, we are going to see shear force and bending moment. This mechanics of material, weightage for the mechanics of material for the gate examination is about maximum 8 marks, means from 4 to 8 marks. And there is a definite question on this shear force and bending moment. 2-mark questions, right? Now first, I will cover the theory part within 5 to 6 minutes. So we know that types of beam: simply supported, cantilever beam, overhanging beam, fixed beam, then supports, roller support, hinge support, and fixed support. So in support, reactions are important. For roller support, we take only one reaction while drawing the free body diagram. For hinge support, we take two reactions, but there is a reason why we take one reaction for the roller support, and for the hinge support we take two reactions. Because in a roller support, we restrict the motion in a one direction. So reaction by the body, whenever we apply the force, we get the reaction, but here in this case motion in horizontal direction is possible, and here rotation is also possible, but vertical motion is restricted due to this roller, right? So motion restricted in one direction means how many reactions, how many motions we restricted, that amount of reactions we need to take, that amount of forces are going to induce on the component. For the hinge support, you can see this is the example of hinge support. For door we use a hinge, right? So in this case we restrict the motion of door in horizontal direction, we restrict the motion in a vertical direction, but rotation is possible, right? So we restrict the motion in a two direction, in a vertical direction, in a horizontal direction. Due to that, there is a two reaction, in a vertical direction and in a horizontal direction. So this reaction depends on how how may how many movements you restrict the, right. And in third, fixed support. This fixed support means permanently fixed by bolting or welding or grouting, right? So here we can't move the beam in X direction, in Y direction. Also, we can't rotate the beam. So we restrict the all three motions. So due to that, here we need to take three reaction: one in the X direction, one in Y direction, and rotation means we need to take a movement also, right? Then types of a load: point load, uniformly distributed load, and last is the uniformly varying load. So these are the three type of a load. Now we'll see concept of shear force and the bending moment. So shear force means it's tangential force which try to shear the object, try to cut the object. That is known as a shear force. And bending moment, that effect of force which try to bend the component. But bending moment is different. In this case, shear force is nothing but the algebraic sum of vertical forces, either left part of a section of a beam, and bending moment is algebraic sum of movement of all forces, either left part of a beam or right part of a beam. I will see the concept of shear force. This is the beam diagram. Two loads acting on the beam, 10 kilonewton and 20 kilonewton. These are the active load, and at A point there is a hinge support, at the D point there is a roller support. Now to take the concept of shear force is nothing but the algebraic sum of vertical forces, either left part of the beam or right part of the beam. We know that this beam is in equilibrium. If we break the beam into two or three parts, each and every part is in equilibrium, right? Means we can apply equilibrium condition for each and every part. Summation fx equal to 0, summation fy equal to 0, summation of movement about any point equal to 0, right? Now we'll see concept of shear force diagram through this example. First, this is the load diagram. We need to draw the free body diagram. Replace hinge support and roller support by the reactions AX, and now this, for this hinge support we are going to take two reactions. AX reaction acting in a horizontal direction, AY reaction in a vertical direction, and at the point D is there is a roller support. So we need to replace this roller support by vertical reaction. Okay. Now to find out this unknown reaction, we should use equilibrium condition. That is, first equilibrium condition is summation fx equal to 0. Treat rightward forces positive, leftward forces negative. So ax equal to 0, because this ax is only one force acting on this beam, right? So here value of x force is a 0. Now we'll apply second equilibrium condition, that is summation fy equal to 0. So treat upward forces positive, downward forces negative. Ay plus dy minus 10 minus 20 equal to 0. Right. So in this way we will get the equation Ay plus dy equal to 30 kilonewton. Now we'll take moment, third equilibrium condition, that is summation of movement of all forces about any point equal to 0. So we'll take movement about a point. We are taking movement about a point to avoid the calculations, because at a point two forces acting. We can take movement at a point B, C, or D, or anywhere we can take a movement. But to avoid the calculations, we need to take movement where number of forces are more, right? So we are taking movement at the point A. Now movement of this 10 kilonewton force about a point, 10 into 2 is 10 kilonewton, and distance is a 2 meter, right? So 10 into 2, and this movement is a clockwise movement. Treat clockwise movement positive, anti-clockwise movement negative. Now movement of this 20 kilonewton force, this movement is a 20 into 4, right? And this movement is also clockwise movement. So I have taken here positive. Movement of this dy force, dy into perpendicular distance is a 6 meter. But this movement is a anti-clockwise, acting in an anti-clockwise direction. So I have taken here negative. So dy equal to 16.67 kilonewton. if we put the value of this dy in this equation, we'll get the value for ay, that is ay equal to 13.33 kilonewton. Okay, now this is the first step to understand the concept of shear force. Now sign convention is important. So for the SF, when we consider the left part of the beam, treat upward forces positive, downward forces negative. If we consider the right part of the section of a beam, then treat downward forces positive, upward forces negative. Okay. Now we'll take a section. Now this section, there is a rule for the section. We'll see later on. Just we are trying to understand the concept of shear force. We are taking shear section at a distance of 1 meter. Then this section divide the beam into two parts, left part and right part. We can select any part, but to avoid the confusion about the sign convention, always consider only left part. Okay. Now if we consider the left part, there is only one force, that is 13.33 kilonewton, which is acting in upward direction. That force is available at the left part only, right? So according to definition of shear force, it is algebraic sum of all vertical forces, either left part of the section or right part of the section. So according to that, shear force at a section 1 will be plus 13.33 kilonewton. Now right part of the section, you can take right part of the section. Okay. Now if we consider right part only, then there are the three forces, 10 kilonewton, 20 kilonewton and 16.66 kilonewton. But for right part, sign conventions are different. Treat downward positive, upward negative. So this 10 is positive, 20 is positive and 16.66 is negative. So once again we'll get the same answer, 13.33 kilonewton. Now by considering left part or considering right part, we found the shear force at a section 1, right? Now similarly, if we take a section 2, just check, if we divide the beam into two part at the section 2, forget about the section 1. If we consider left part, there will be two forces. One is upward, one is downward, right? Apply the sign convention. So this 13.33 is positive, and 10 is a negative because it is acting downward direction. So shear force at section 2 is a 3.33. If we consider say right part of the beam, we'll get the same answer. In this way, if we take a section 3 at a distance of 5 meter, and if we do the shear force calculation for the left part and right part, we'll get the same answer, right? So shear force is nothing but the just algebraic sum of vertical forces, either left part of the section of a beam or right part of the section of a beam. This is because this beam is in equilibrium. If we divide the beam in n number of parts, then each and every part is in equilibrium, right? So this shear force get balanced. Then now we'll move for the bending moment. Bending moment is nothing but the algebraic sum of movement of all forces. So bending moment is the algebraic sum of movement of all forces, either left part of the section or right part of the section. Now we'll take same example. We'll see how to calculate the bending moment here. Once again, I will take a section at a distance 1 meter from the left end. Give the name say section 1. Now bending moment, according to definition, bending moment, Bending moment, it is the algebraic sum of movement of all vertical forces, either left part of the section or right part of the section. Now this section divide the beam into two parts. This is the left part and this is the right part. Okay. Now we need to consider only one part. Now we consider the only left part. In the left part, there is only one force, that is 13.33 kilonewton, and that force acting in upward direction. Now, according to definition, we need to take movement about the section. So, movement of this 13.33 kilonewton about section 1 is 13.33 into 1 meter distance, right? And according to sign convention, treat clockwise movement positive, anti-clockwise movement negative if we consider the left part of the section. Okay, now we'll see for the right part also. Now forget about the left part, just focus on the right part of the section. In the right part, there are the three forces: 10 kilonewton, 20 kilonewton, and 16.66 kilonewton, right? So means to calculate the bending moment at a section 1 we need to consider three forces. We need to take a movement of three forces: movement of 10 kilonewton force, movement of 20 kilonewton force, and movement of a 16.66 kilonewton force. So movement of 10 kilonewton force about the section 1 So this section 1 is a movement line, or we can say this is the movement center. So movement of this 10 kilonewton into 1 meter distance, right? And this movement is a clockwise movement. This movement is a clockwise movement, right? But we have considered the right part of the section. For the right part, treat clockwise negative and anti-clockwise positive. So due to that, this 10 kilonewton meter movement is a negative. Now movement of 20 kilonewton force, this force into distance, 2 into sorry this 2 plus 1 meter means total distance is a 3 meter, so 20 into 3 meter, and this movement is a clockwise about the section 1 So due to that, here I have written minus 20 into 3, right? Now movement of third force, that is 16.66 kilonewton. This movement is acting in an anti-clockwise direction, right? So due to that, I have taken here positive sign as per the sign convention, and distance is 5 meter, right? And if we do the calculation, we'll get the answer 13.33 kilonewton meter. Now check left part answer and right part answer, both answers same. Now if we take a section 2 if we do the calculation for the bending moment at a section 2 for left part and for right part, we'll get the same answer. Then for section 3 just try to solve for the section 3 and put your answer in a chat box. You need to solve only one part, left part or right part. Just try to solve it and put your answer in a chat box. Try to calculate bending moment at a section 3. Bending moment is nothing but the algebraic sum of moment of all forces, either left part of the section or right part of the section. 16.66, right? Sixteen point six. Is it positive or negative? 16. Okay. Okay, right. Now we'll see where to take section for the SF calculation and for bending moment calculation. We can take section anywhere in a load diagram, but to avoid the calculations and complications, we need to consider certain points. So there are the rules for the SF section and bending moment section. So first, consider left or right part of a section for calculation purpose. Generally, we consider left part to avoid the confusion about the sign convention. Then next, SFD. SFD means variation of shear force along the length of beam, and bending moment. BMD means variation of bending moment along the length of beam. So here I have shown the SF diagram and a bending moment diagram. So along the x-axis, we plot the length of a beam, that is in a meter, and along the y-axis, we plot always shear force in the kilonewton. Okay, and for bending moment, we plot length along the x-axis and bending moment, that is in a kilonewton meter, along the y-axis. Base of SFD and BMD diagram is always equal to length of a beam, right? Positive value of SF and bending moment are plotted above the baseline. Negative value below the baseline. SF value should be calculated at all critical points. So we should not avoid these critical points. First critical point is just before and after vertical load. Means we need to take a section just before and after the any vertical load or point load. Second, just at a start and end point of a UDL and UVL, right? Uniformly distributed load, uniformly varying load. Now we'll see the critical points to draw the bending moment diagram, or to take a section on a load diagram. First critical point, at point load, we need to take a section. Second critical point, just before and after concentrated movement, we need to take a section for the bending moment. Third critical point, just at a start and end point of a UDL and UVL. And fourth, where SF changes its sign, means whenever SF changes from positive to negative or negative to positive, at that point also we need to calculate bending moment. Calculate maximum bending moment in a UDL and UVL span. So these are all the critical points we must consider while taking the section. While solving the problem, we'll see the significance of these all critical points, why we should take these critical points. Okay, now sequence of a diagram. First we need to draw load diagram, then free body diagram, then SF diagram, and then the bending moment diagram. Then next point is a point of counterfracture. This point of counterfracture where bending moment changes its sign. So in previous diagram, we can see bending moment changes its sign from positive to negative. So this point is known as a point of counterfracture. Means there is actually drastic change. Now we'll see the nature of SF diagram and bending moment diagram. Between point load, SF diagram is always horizontal line. There is a logical reason. We'll see later on through example, through derivation. Okay. And bending moment nature, whenever between point load is a straight inclined line. For concentrated movement, whenever there is only two concentrated movement acting on the beam, then nature of SF, that concentrated movement doesn't affect the SF, because definition of SF is it is algebraic sum of vertical forces. So this movement doesn't take part in a shear force calculation, or it doesn't affect the shear force value, right? So that nature remains same. And for the bending moment diagram, between concentrated movement is always horizontal line. Whenever UDL load is on the beam, then SF nature is an inclined straight line, and bending moment nature is a second degree curve. So there is a logical reason, there is a derivation for this inclined straight line or second degree curve. Why we should draw inclined straight line for a UDL loading and second degree curve for the bending moment diagram, right? Then third one is if load is a UVL, for the UVL span we need to draw a second degree curve for the SF diagram and third degree curve for the bending moment diagram. Okay, there is a logical reason, there is a derivation for this second degree and third degree nature of a SF and bending moment. Okay, we'll see while solving the derivation or during the problem. Okay, now first we'll solve one problem to understand the nature of SF and bending moment. So draw SFD and BMD for simply supported beam with a point load W at the center. Okay, so this is the simply supported beam and load W is acting at the center, means at a distance of L by 2. Length of a beam is a L meter. Okay, now first draw the free body diagram. While drawing the free body diagram, we need to replace this hinge support and roller support by the reactions. So here I have replaced the hinge support by two reactions, AY reaction, AX reaction, and roller support by the CY reaction. Okay. Now to find out these unknown forces, we need to use equilibrium condition. Summation Fx equal to 0. So by using this summation Fx equal to 0, we'll get Ax equal to 0. Summation Fy equal to 0, we'll get Ay plus Cy. Ay plus Cy minus W equal to 0. And if we take moment about point A equal to 0, moment about point A equal to 0. So moment of this W force W into L by 2, and it is clockwise. So this moment is a clockwise. Then minus Cy into L. Moment of Cy force is a Cy into distance L, and moment of this Cy is a anti-clockwise. If we do the calculation, we'll get here Cy equal to W by 2. If we put the value of Cy in this equation, we'll get Ay equal to W by 2. Actually, by observation also, we can write the value of Ay and Cy, because W is acting at the center only, and that load will be divided into two equal parts at Ay and Cy, right? Because Ax equal to 0. So value of Ay is W by 2, value of Cy is a W by 2. Now we'll see the SF calculations. Now for SF calculation, we need to draw load diagram and we need to consider all critical points. So as per the rules of critical points, we need to take section just left of point load, vertical load, and just right of a vertical load at the start of UDL at the start of UL, at the end of UL, at the end of UDL. But here on the given load diagram, there are only vertical loads acting, no UDL, no UVL, right? So here at this left end there is a vertical load, that is W by 2. So we need to take section just left of A, just left of B. Let this point is A, this point is a B. Sorry, this point is a B and this point is a C. Okay, so SF at a section 1 1, or we can say SF just left of A. Now consider section 1 1. Now this section divide the beam. Okay, but beam goes in a right part, at the left part there is no beam portion. So there is no beam portion, so we can directly say shear force value is 0, right? Now consider section 2 2, just right of this A. Okay, if we consider section here, now that section divide the beam into two parts, left part and this is the right part. Okay, now forget about this section 1 1, and we need to consider only one section, either left or right, but we always consider left part to avoid the confusion, right? Okay, so consider left part of the section 2 2. So there is only one force, that is W by 2. Okay, and that force, see the sign convention. If we consider the left part, treat upward forces positive, downward forces negative. So this W by 2 force acting in a upward direction. So value is SF at a section 2 2 is a W by 2, and that value is positive. Okay, now consider section 3 3. This W is also point load or vertical load. Due to that, we have taken section 3344. Section 33 just left of this W load, and section 44 just right of this W load. Okay, so now consider section 33, SF at a section 33, or we can write SF just left of B, means SF at this point. Okay, now consider only left part, forget about this section 1 1 1 and 2 2. Now there is again only one force, that is W by 2, and it is acting in upward direction. So W by 2 kilonewton positive. Okay, shear force at a section 3 3 is a positive, and that magnitude is W by 2 kilonewton. Now consider section 4 4. At a section 4 4, or we can say SF just right of B. If we consider section 4 4, now forget these three sections and consider only left part for the calculation. So there are the two forces. One is W by 2 acting upward, and another is a W force acting downward. According to sign convention, treat upward forces positive, downward forces negative. Okay, so this W by 2 is positive and minus W, because it is acting in a downward direction, right? So we'll get answer here, minus W2 shear force, minus W by 2 shear force. Okay, now SF at a section 5 5, you can see here at the 3 3 point we got the value W by 2, that is positive, and at a 4 4 section 4 4 we got the value minus W by 2. Means whenever there is a point load, there is a drastic change in a shear force. So due to that, we always consider section just left of the vertical load and just right of the vertical load. Then next, section 5 5. So we have taken section 5 5 at just left of this C point. Now divide the beam into two parts. This is the left part and this is the right part. Okay, if we consider the left part of the beam, there are the two forces, W by 2 acting upward and W acting downward. According to sign convention, shear force at section 5 5, W by 2 minus W, so minus W by 2, right? Okay, now last section, section 6 6, just right of the C point. If we take section here, beams goes in a left part. At the right side there is a no beam portion, so we can directly say SF66 equal to 0. If we do the calculation for the left part, then also we'll get the shear force value at a section 66 equal to 0. So this is related to the shear force calculations. I hope everybody understood. If you have any doubt, please ask. So we can move for the next bending moment calculation. If you have any doubt, please ask. Do we understood or not? Please put a message in the chat box. Calculation of SF. Hello Akash, do you understood? Omkar, Pallavi. Yes, now we'll move for the bending moment calculations. Now you can see here for the bending moment. I have taken 3 sections. As per the rule of critical points, we need to calculate bending moment at all vertical load, then UDL start point, UVL start point, UDL end point, UVL end point, and just left and right of a concentrated movement. And another point is where SF changes its sign, right? But in this diagram, we can see there are only vertical loads. There is no UDL, no UVL, right? So according to rule of critical points, we need to take a section at vertical loads. So I have taken section at this W by 2 load. I have taken section at W load, and third section is at a W by 2 load, right? So there are the 3 sections. So 3 sections according to critical point rule and sign convention. If we consider left part of the section, then treat clockwise movement positive, treat anti-clockwise movement negative. If we consider right part of the beam, then treat anti-clockwise movement positive, clockwise movement positive, right? Now consider section 1-1. If we consider section 1-1, beam goes in a right part. In a left part, there is no beam portion. So we can directly say bending moment at a section 1-1 equal to 0, right? But if we consider right part and if we solve for the right part, then also we'll get the answer 0. Then now bending moment at a section 2-2. Bending moment at a section 2-2, divide the beam into 2 parts. Forget about section 1-1. Forget about this section 3-3. Okay. Now just focus on section 2-2. It divides the beam into 2 parts. This is the left part and this is the right part. Now, according to bending moment definition, it is just algebraic sum of movement of all forces, movement of all vertical forces, either left part or right part. Here we have considered left part. So in left part, how many forces acting on the beam? Only one force, that is W by 2. So to calculate the bending moment, we need to take moment of this force. Moment of this force is W by 2 into L by 2 distance. W by 2 into L by 2. So in this way, we'll get the moment WL by 4 kilonewton meter. Right. So bending moment at a section 2-2 is WL by 4 kilonewton meter. And now we'll move for the section 3-3. If we take a section 3-3 at the end point, and if we divide the beam portion, so whole beam portions goes to the left side. At a right section of at the right part, there is a no beam portion. So we can say directly bending moment at section 3-3 equal to 0. If we do the calculation for the left part, then also we'll get bending moment 0, right? So this is related to the bending moment. Okay, now we'll see how to draw the SF diagram and bending moment diagram. Now, SF diagram, first we need to draw the load diagram, then pivot diagram, and as per the SFD diagram rule, that base of SF is equal to the length of a beam. That SFD means variation of shear force along the length of a beam. So we, through this SF diagram, we always check the variation of shear force along the length of a beam. So here for SF diagram, first we need to draw the baseline, that is AC line, which is equal to L meter, right? Then SF just right of A is equal to W by 2 kilonewton. SF just left of A is 0. So here we have drawn the W by 2 vertical line. That is vertical shear force. Okay. But from A to B, or we can say from section 2 to section 3, value remains same. So here in this zone, value of shear force is W by 2, because if we take a section here, only one upward force is there, that is W by 2, right? So due to that, shear force value remains same up to the B point. But at a B point means when we take section just right of B, then shear force value changes, that is minus W by 2. So here at the right of B, we'll get the minus W by 2. So join this W by 2 with minus W by 2. Okay. Then next value is SF at a section 5 or SF just left of C. That value is again minus W by 2. Means if we take a section here, section at the extreme end, then value of SF is a minus W by 2. So value of SF at a B point is minus W by 2. Just left of C is also minus W by 2. So we can join with the horizontal line, right? And then at the end, SF value is 0. So in this way, we can draw the SF diagram. Now we'll see how to draw the bending moment diagram. Okay, this is the bending moment calculations. Now bending moment diagram, you can see here at A point bending moment is 0. At a B point, sorry, at a C point, mean at a section 3 bending moment is a 0, right? But at a center point, value of bending moment is a WL by 4, right? Now here we have joined in SF diagram, we have joined the A and B point through this horizontal line, but here we have taken inclined line. You can see here at B point we got the value WL by 4. Suppose if we take a section at a distance of this L by 2 distance, okay, if we take a section at L by 2 distance and we calculate the bending moment, at this point we will get the value is W by 2 into L by 2, means we will get the value WL by 4, which is, sorry, WL by 8. We'll get here value WL by 8, because this distance is already L by 2. If we are taking section here at a distance of L by 4, then this is L by 4, this W by 2 into L by 4. So at this section, at this point, we'll get the bending moment WL by 8. Means there is a something positive value, and this value is proportional to this WL by 4 value, right? So this will be on a straight line, or I will give one another example. Suppose we take a section, any section in between this A point and B point, and this section is at a distance x. Okay, this section is at a distance x. Suppose we write a bending moment equation. We'll at a section x distance, we'll get here W by 2 into bending moment equal to W by 2 into X, means bending moment equation varies with respect to X, and that is the straight line equation. Due to that, here we need to draw inclined straight line. Once again I will repeat, if at intermediate point between A and B, if we take a section at a distance x, and if we calculate the bending moment, we'll get bending moment W by 2 into x, and this x we can vary from 0 to L, right? Okay, so means this bending moment equation will become bending moment at a section SS equal to W by 2x, and that's W by 2x indicating that that is the equation of a straight line. So due to that, we always join straight line. We always join the points with a straight line whenever there is a point load in a load diagram. So for bending moment, here we have drawn straight inclined straight line. Here also we have drawn inclined straight line. So value is here WL by 4, and at the C point value is 0. If anybody having doubt, please ask. Do you understood concept of shear force and bending moment, or nature of shear force diagram, or nature of bending moment diagram? Okay, now we'll move for the next. We will solve one problem. So we'll get idea about the calculation of shear force, bending moment, and how to draw shear force diagram and bending moment diagram. So this is the load diagram is given in the GATE exam. Generally, question is like that: find out the shear force at a point C, find out the bending moment at a point D. Then nature of SF diagram between region C and D, nature of bending moment diagram between region D and E, like this. Okay, so this is the load diagram. Now first we need to draw the free body diagram. Replace this hinge support by the two reactions, replace this roller support by the vertical reaction. Okay, now calculate the unknown reaction. To calculate the unknown reaction, we need to consider equilibrium conditions. Three equilibrium conditions: summation fx equal to 0, summation fy equal to 0, summation of movement about any point equal to 0. Already we studied in engineering mechanics that for the non-concurrent coplanar forces we use three equilibrium condition to find out the unknown reaction. Okay, now by using summation fy equal to 0, we can write the equation ay plus dy minus 10. Sorry, yes, right, minus 10. And if we take a movement about point A, we can take movement about any point. But to avoid the calculations, always take movement where number of forces are more. So if we take a movement about point A, we'll get the answer for the dy for this roller support. So dy equal to 3 kilonewton. If we put the value of dy in this equation, we'll get the value of ay, that is 7 kilonewton. Okay. Now here, movement about a point. So movement of dy force about a point is, this movement is a anti-clockwise. This dy force into distance is a 6 meter. So due to that I have written here minus. Okay. Now this 10 kilonewton meter and 12 kilonewton meter, these are direct concentrated movement. We need not to multiply by the distance. Just we consider the that direction of movement. This 12 kilonewton meter movement acting in a anti-clockwise direction. Due to that, I have taken here minus 12, and this 10 kilonewton meter acting in a clockwise direction. So I have taken here positive. Okay. If we solve this equation, we'll get the answer dy equal to 3 kilonewton and ay equal to 7 kilonewton. Now we'll move for the SF. Always, please keep in mind, we need to take section on a load diagram only. Never take section on a free body diagram, because in a free body diagram we replace UDL and EVL by the point load, but their effect is different. UDL effect is different. So for that purpose, we need to take section on a load diagram only. Now, according to section of critical point rules, we need to take a section just before the point load, just right to the point load. So in this load diagram, there are the 3 point loads. This AY, that is 7 kilonewton, this 10 kilonewton, and DY is a 3 kilonewton. Okay, and there are the 2 moments. Okay, now first section is just left of this point load, just left of vertical load. If we take section here, then apply the sign convention. If we take a section 1 1, and if we divide the beam goes in the right part, in the left part there is a not any single portion of a beam, so we can directly say SF equal to 0. Now take a section 2 2 just right of A. Now divide the beam into 2 parts. Forget about section 1 1 and consider only left part. For the left part, this AY force is acting in upward direction, and according to sign convention, for the left part, upward for treat upward force is positive. So for the section, sorry, SF at section 2 2 will be plus 7 kilonewton. Now section 3 3, just left to the next vertical load. Okay, section 3 3 here. Now forget about section 1 1 and 2 2. Divide the beam into 2 parts, left part and right part. Focus on left part only. Apply sign convention. So in left part, only one force, that is 7 kilonewton, and it is acting in upward. Shear force means it is algebraic sum of vertical force only, right? So according to this, 7 kilonewton shear force will act at a section 3 3. Now take section 4 4, just right off this vertical load. Now this section 4 4 will divide the beam into 2 parts, left part, right part. Consider left part only. In the left part, there are the 2 forces, 7 kilonewton acting upward, 10 kilonewton acting downward. Use sign convention. As per sign convention, we'll get here SF value is minus 3 kilonewton. Then for the concentrated movement, we need not to take a section. If we take section here, then also okay, but it our time will go, because here we need not to take a section, right? If we take section, answer will remain same. If we take section, just write up C also, that answer will remain same, that is 7 kilonewton, because this movement doesn't affect the shear force. Now due to that, we have taken a section here 5 5 just left to the vertical load. Now we'll see the calculation. If we take a section here 5 5 and consider the left part, only 2 forces, 7 kilonewton upward, 10 kilonewton downward, so we'll get same answer. Now section 6 6, at a section 6 6, if we consider this section 6 6, divide the beam into 2 parts, left and right. For the left part, there are the 3 forces, 7 kilonewton, 10 kilonewton, and this 3 kilonewton also, right? So but if we consider right part of the beam, there is no vertical force, so we can directly say SF at a section 6 6 equal to 0. If we do calculation for the left part, then also we'll get same answer, that is 0. Okay, so this is related to SF calculation. Now we'll go for the bending moment calculation. Again, we are considering the same beam, but section critical point are different than the SF critical points. For the bending moment, we take a section at a point load. We take a section before and after the concentrated movement. Okay. So we have taken section 1 at this point load, and consider this section. Please keep in mind this sign convention rule, sign conventions. This section 1 divide the beam. Now beam part goes in a right up section. In the left up section there is no beam part. So bending moment at section 1 equal to 0. Okay. Now we'll take section 2 at next vertical load. Section 2. Now forget about section 1. Divide the beam into two parts, left part and right part. Okay. Now for left part there is only one force, that is 7 kilonewton. According to definition of bending moment, we need to take movement of this 7 kilonewton force. That movement of this 7 kilonewton force is 7 kilonewton into 2 meter distance, and this movement is acting clockwise about section 2. According to sign convention, for the left part of a section, consider clockwise movement positive, consider anticlockwise movement negative. So here this bending moment at a point B. Okay. Now take a section 3 just before the concentrated movement. Now divide the beam into two parts, left part and right part. Consider only left part. Forget about these first two sections. Now do the calculation bending moment at section 3. Now there are the three forces. One 7 kilonewton, sorry, two forces. One 7 kilonewton, another is a 10 kilonewton force. Take a moment of 7 kilonewton force. 7 into 4 about section 3. 7 into 4, and this movement of 7 kilonewton force is a clockwise about the section CC, right? And now take a movement of this 10 kilonewton force about section CC, about section 3. This movement is anti-clockwise, 10 into 2 meter distance, right? So in this way here we'll get the answer 8 kilonewton meter positive. Now section 4 just to the right of concentrated movement. Now we'll see the calculation. Just write off this at a section 4. If we consider the left part, there are the two forces, 7 kilonewton, 10 kilonewton, and there is a 12 kilonewton meter concentrated movement is also there when we consider section 4. So take a moment of 7 kilonewton force, 7 into 4, and movement is clockwise, so positive. Then movement of 10 kilonewton force into distance 2 meter, right? But it is anti-clockwise. So here I have taken negative and minus 12. Why minus 12? Because this movement acting in the anti-clockwise direction. So minus 12. So finally I got the answer here, minus 4 kilonewton meter at a section 4. You can see here at a section 3 means just left of concentrated movement, bending moment is 8 kilonewton meter, and at a just right of C point, bending moment is a minus 4. So there is a drastic change in a bending moment. Due to that, we need to take section just left and right of a concentrated movement, because according to definition of a bending moment, it is algebraic sum of movement of all forces. Whenever there is a concentrated movement at the left side, that movement doesn't take part for the bending effect, and at the right part that movement take part in a bending movement, right? So due to that, this we need to take section at just left and right. Now next further section will be at vertical load, that is at a point D, section 5. Now we'll do the calculation for the section 5. Now there are the two forces, and third one is a movement of a 7 kilonewton force, 7 into 6 meter, 7 into 6, and this movement is clockwise. Now movement of 10 kilonewton force, 10 into 4, and movement is anti-clockwise. And third, concentrated movement 12 kilonewton meter, but it is anti-clockwise direction. So minus 12 equal to minus 10 kilonewton meter. Okay. Now next, here is the concentrated movement. So we need to take section just left, just right at a section 6 6. Now for this section 6 6, instead of this left part, we can consider directly right part. If we consider right part, there is a clockwise movement. But if we consider right part, for the clockwise movement, sign as per the sign convention, we need to consider negative. So here answer is minus 10 kilonewton meter. If we solve by the left part, then also we'll get the same answer. Here actually I have solved with the left part, but simply if we consider the right part, there is only one movement, so we can get answer easily. So this is about the bending moment at a section 6 6. Okay, then bending moment at a 7 7. Now if we consider this section 7 7, beams goes in a left side. At the right side there is no beam portion. So if we consider right part, bending moment will be 0. So at a section 7 7, bending moment will be 0. Now we'll see how to draw the shear force diagram. So I will take here SF calculation. SF at one point. First we'll draw the baseline and draw all the critical points A, B, C, D and E. Then SF value at just right of A is a 7 kilonewton. So due to that I have taken here vertical line of a 7 kilonewton. Then for next point also 7 kilonewton up to the B, and just right of B shear force value is minus 3 kilonewton. So I have taken here minus 3. Then we have taken section just left of D, and at that point we got the answer minus 3 kilonewton, same answer. And bending shear force at the right of D equal to 0. So just we need to join sequentially to draw the SF diagram. Now we'll see bending moment diagram. This is the calculation of a bending moment. Draw the baseline first, point all critical points, then bending moment at a point B. Sorry, here I have written A. Bending moment at a point B is a 14 kilonewton meter at this point. And we know that between point load, bending moment diagram is a straight inclined line. So this is 0, and at this point B is a value is 14 kilonewton meter. Okay. Then at a C point, just left of C, we got the value 8 kilonewton meter. So join with the straight line, but there is a drastic change due to the movement. At just right of C, we got the value minus 4 kilonewton. So join with the straight line. Then next minus 10 kilonewton meter at the D point. At the D point, we got the value minus 10 kilonewton meter, and we join the bending moment diagram with the straight line between vertical loads. Now, just left of E, again we get the same answer, minus 10 kilonewton meter. So here we need to draw with the horizontal line, and at right of E means at E point, bending moment equal to 0. I hope you understood. If you have any doubt, you can ask. If you have any doubt, you can ask. Please ask. This is related about the how to draw SF diagram, bending moment diagram, how to do the SF calculation, bending moment calculation. Whenever vertical load and concentrated movement acting on the beam diagram. If you have any doubt, you can put a message in the chat box. Do you understood? Just fill up this feedback form. If you have any doubt, you can ask. In next section, we'll see how to draw the SF diagram, bending movement diagram for the UDL and UVL. Please fill up the feedback form and put a message in the chat box. Whether you have filled or not, please put a message in the chat box and then you can leave the class. It takes only 2 minutes.